as I say, it's Xray crystallography, macromolecular crystallography, and for the last 100 years, Xray has contributed tremendously in various fields of sciences like chemistry, physics, biology, forensic sciences, medical sciences, and it all started with the discovery of X-ray by Röntgen. And we all know that in science, chance favors a prepared mind. Since Röntgen was working with discharge tube, and he saw that a cathode ray, when falls on metal ion called anti-target, it produces an unknown kind of ray, and he called it as X-ray. And later it was found that the wavelength of this thing is of the order of angstrom. So after this discovery, say about 1 decade after this discovery, Röntgen Brax discovered that X-ray could be reflected by a set of plane formed by atoms in the crystals. So it was the first foundation stone of crystallography, and later, say from 1912 to 1940, 50, at this region, people solve structure of benzene, small molecule, salts, and this thing. But apparently, it looks that it is worthless or it is not of that important. But from these studies and from the studies of the peptides, small peptides, dipeptides, Pauling and Corey established the foundation stone of protein crystallography because they deduced all the bond length, bond angle so correctly that it can be applied to modern structure determination. So these are some timelines. Already I told about X-ray, discovery of X-ray, then Röntgen, then Brack's law. Then actual macromolecular crystallography started from 1953 to 1960, this period, when the structure of hemoglobin, myoglobin was solved. Now, if you see in the PDD, an year-wise release of data structure, we see there's NMR up to 2006, 2007, it was going fine. Then now it is showing a declining trend. Whereas EM, if I see, EM, you see, it is rapidly picking up from the year of 2015-16, and while X-ray, you see, that is keep on increasing even today. Now, these are the three different methods, NMR, X-ray, and EM, in solving the structure. Each method has some advantage and disadvantage. Suppose if we consider NMR, solve the structure in solution, as while in X-ray or in EM, it is either in crystal form or in other form, but not in solution. Or if we talk about the molecular size, X-ray has no limit practically, so it can solve any big protein structure. Whereas for NMR, it is 20 to 30 kD, the range. Whereas EM only can solve large assembly, but it cannot solve small molecule. We need at least 150 kD to solve by EM structure. Below that, it will be not good, or it will be not possible. Whereas X-ray can solve salt structure, solve crystal to very big protein structure. So it has a tremendous choice. So again, in NMR, you can talk about the dynamics of the protein, whereas X-ray structure and EM structure are static. Again, in NMR, you need huge amount of sample, as X-ray, you need moderate amount of sample, and EM, even you need very small amount of sample, and this is very, very useful in case of membrane proteins, because the yield is very less, and the membrane protein size is very good. So this is mostly the choice of EM with membrane proteins, and the structure we are getting, we are seeing in EM is mostly membrane protein structure. This is again a comparative study of protein of structure solved by X-ray, NMR, and EM. So far, 1,60,000 structure has been solved by X-ray, which covers this region. NMR, this region, this is 13,000, or EM is 8,000. This is some kind of subdivision. This is up to this protein only, protein DNA, protein carbohydrate, and only protein, only DNA. This kind of division, but overall, this is the distribution. So what we do, the crystallographer do, we need an X-ray source. Then we irradiate a crystal with X-ray and see the diffraction pattern. So from this diffraction pattern, it is like this diffraction pattern. We calculate electron density and ultimately solve the structure. Now, last few decades, tremendous improvement has been done in the X-ray sector. So the source of X-ray has improved a lot, and detector also has improved a lot. And in between the data and electron density map, the phase problem is there. And there are various methods in solving the phase problem. And that is that all these things contributed tremendously to solve the protein structure. And that is the huge amount of structure we see per year. That is all the outcome of this thing. Moreover, for crystallography, we need a purified protein. Now, this molecular biology technique has improved a lot, so the huge amount of protein is not a problem, at least for soluble protein. Okay, so why you need a crystal? Basically, X-ray, when falls on an atom in the crystal, it interacts with the electron of the atom. And if we all know that in case of protein is made of carbon, nitrogen, and oxygen, and sometimes sulfur or some metal ion. But by and large, the atoms are all low molecular weight, so they have very less number of electrons, 6 to 8. So that is, if we consider a single atom, the diffraction we see is very feeble, and it is very difficult to detect. So what the crystal does, it is a three-dimensional repeated arrangement of atoms in every direction, three-dimensional repetition. So if we radiate with X-ray, the signal we got is an amplified signal. So crystal basically acts as an amplifier. Okay, so before going to the details in crystallization in this part, let me introduce about protein structure in one slide. So we know proteins are made of amino acid, and it has a carboxy group and an amino group, and one amino acid attached with another amino acid through this condensable group, and they form a peptide bond and water is released. So basically it's a condensation reaction, and this way the combination of different proteins, different amino acid in a polypeptide chain dictates the nature of the protein. But whatever be the nature, let me tell you that this acidic group, say positive charge group or negative charge group, they mostly reside on the surface, while the hydrophobic group, they reside inside the protein mostly. Moreover, once they condense to form the polypeptide chain, all the condensable or the reactable group are engaged. Now, why the fold? The folding actually comes from this CO and NH group interaction. So some cases from alpha helix or some beta sheet, but overall they fold in a globular protein. All the hydrophobic residue goes inside mostly, and the charge residue like plus charge and minus charge, they reside on the surface of the molecule. So this is, say, one protein molecule, say, and the surface has a mosaic of positive and negative charge. There's no pattern as such, and they are tumbling in a solution, and we want to crystallize it. Now, suppose it is tumbling in a solution and you want to crystallize, means suppose it can crystallize like this, it can crystallize like this, and these are typically, I would say, it is space group, defined space group, say it is in crystallized in defined space group. So here it is in crystal, this form of crystal or in the form of crystal, it is ordered, whereas it was disordered in the solution, starting solution. So if we go from this state to this state, the del S would be negative. So whole TdS term would be positive. But if the crystallization goes continuously, then del G has to be negative. So in that case, del H has to be large negative value to compensate TdS value. So that's why you see there is lots of plus minus interaction in the crystal. So this plus minus interaction mostly dictates the crystallizability of a protein molecule. So how do we crystallize? So why we are talking about so much about crystallization? Because as I told in previous slides that you need a crystal for Xray diffraction. So without any crystal, you cannot do crystallography. And to produce the crystal, you need large amount of your protein sample and choose a buffer in which your protein sample is soluble. If the protein is not soluble or it's heterogeneous, you will never get a crystal. So try to look a healthy protein buffer where the protein is soluble. And then the soluble protein, you try to bring it to supersaturation where spontaneous nucleation can take place. So to bring it to supersaturation, we use different kind of salts or different kind of parameter to crystallize it. Some of them are physical parameter like gravitation, temperature, even methodology, which methodology you are using, viscosity. Some are chemical, is what kind of precipitant you are using, what pH you are using, what buffer type, even the pH is same, what kind of buffer you are using, that all can affect your crystallization. And this is in the protein level mostly. You have to do, your samples should be very pure and it should be homogeneous. Homogeneous and purity apparently looks close, but purity and homogeneity means, say, oligomerization tendency, different kind of oligomer. Even the protein is same. There is no other protein. So this is heterogeneity or homogeneity. You can modify a sequence, but you can do chemical modification to your protein. Suppose your protein has surface cysteine, and you want to crystallize that, but in solution, one surface cysteine formed a sulfide bond with another molecule, and that will hamper your crystallization. So the best way is to mutate the cysteine, and most probably the people do cysteine to serine or cysteine to alanine and see if it is surface cysteine, and then proceed on crystallization. PI will come little later, ligands cofactor also will come little later. So the purity of the protein, and so you have to purify the protein in the SDS space. Mostly you see a single band, even though with time the protein can develop some heterogeneity. What kind of heterogeneity? Like partial proteolysis product. Recently I have purified one protein. It was a single band and no protease was used elsewhere. But you see, after a few days, the protein has degraded. And if we add PMSF, a serine protease inhibitor, the degradation is stopped. So during purification process, somewhere a little amount of protease was in the protein preparation, and that damaged my protein. Next is oxidation of cysteines. There are some cysteine on the protein molecule that gets oxidized to SOH or sometimes SO3H in extreme cases. So you need to stop that oxidation sometime to get a good crystal or to retain the function even. Deamidation is another case, post-transitional modification is another case, and oligomerization is another form. Say, suppose you purify a protein, how do you check it, oligomerization? Suppose you purify a protein and do D-less, and you see a single band, say, single peak. But after a few days, you see the protein solution is not showing a single peak, that is a mixture of peaks. So you have to say that with time, it is producing different kinds of oligomer. And if you want to crystallize one form of this, you have to stop that oligomerization to a particular form and try to crystallize. And that is protein concentration. As I told, the protein solution has to be a supersaturation level. So you need to have a concentrated protein, and you judge the concentration by extinction coefficient or by photoassay. Sometimes you have cloned the protein and you don't see expression. In that case, maybe your protein is hypoteroxis, or your plasmid mRNA is unstable, or so protein is going into the precipitate insoluble form. So you have to find out a way to make it in soluble form. And this is another one. Some codons are rare in E. coli, so that might give you a misfolded protein or even low yield. So you have to take care of all these things, purify the protein, concentrate it, and go for crystallization. Okay. During crystallization, what we use, sometimes we use a salt. And if we see a solubility of a protein and salt concentration, we see a dome circuit curve or this kind of curve. When there is no salt, solubility is less, and you add little amount of salt, solubility increases, and after some time, solubility again drops. So this portion where solubility increases, we call it salting in, and where solubility decreases, we call it salting out. So you can use this idea to crystallize protein. Suppose you are here and you are still increasing salt. That means the rest amount of protein, this is protein solubility and this is salt concentration. So remaining amount of protein will have to come out from the solution in the form of crystal. Or you are here and you are decreasing salt concentration, then also you can do this thing, that you can get crystal. So you have to choose which way you want to go. Mostly people go in the salting out region. Another variable in protein crystallization is pH. We are familiar, probably you are familiar with the term pI. pI means a particular pH where the net charge of the protein is 0. So if you move net charge of the protein 0, so the net charge is 0, but the total charge is not 0. But if you move either side of the pI, say this side or this side the protein will be negative charge, and if you go this side, protein will be positively charged. So if you are away from pI, the protein will be charged. So in solution, one protein molecule cannot come close to another protein molecule because they will repel each other. That means they will remain in solution and you can concentrate it. But at the point of pI, the net charge is 0. So one protein molecule can come close to another protein molecule, and it may so happen that positive charge of one molecule can interact with negative charge of another molecule, and they form aggregate. That's why we see in pI, solubility is very less. While you go 1 pH or 2 pH above the pI or below the pI, then the solubility increases. And this is mostly governed by this law, Anderson-Hasselbalch equation. So if your protein pI is say 6 and you go to pH 7, you have 90% chance of getting this form. Or if you go to pH 5, you have mostly 90% chance of getting this thing. So it is always better to go 1 or probably 2 pH higher or lower of either side of Pi to get a very good solution for crystallization, very good concentration for crystallization. Whereas if you try at Pi, solubility is very less and there is less chance of crystallization, crystal formation, and you get amorphous precipitate. And the funny thing is, so far the 10,000 or more crystal has been solved and crystal has been grown, different form of crystal has been grown. None of them has been grown at Pi. So one factor is salting in, salting out, salt, and that is Pi, and another is temperature maybe. Suppose you are trying to crystallize a protein molecule, you are trying to make it order, and if you increase the temperature, so they can move in the solution rapidly, or there will be variation of movement. So that can affect crystallization. Moreover, we use a crystallization chamber like this incubator like this, and this incubator is quite different from other incubator we use for in the laboratory. In those incubator, you have a condenser. So compressor. So you have a compressor in that. In the other, so the compressor keep on and off, and this creates vibration. And we are trying to create a crystal in ordered form, and this ordered form formation and this vibration, it goes against each other. So we have to use a special kind of incubator. Is a Peltier-based incubator. There is no compressor. And you can use 2-3 different temperature to set your crystal drop. Different temperature, protein solubility different, and so the equilibrium will be different also. Okay, so what kind of precipitant to use for crystallization? Generally, we use high soluble salt, like ammonium sulfate, lithium sulfate, some nitrate. They are sodium chloride, they are highly soluble. And so you can use at high concentration to precipitate a protein in the salting out region. If the salt is sparingly soluble and you use that for crystallization, instead of getting protein crystal, you might see a salt crystal after a few days. So it is advisable to use salt which has very high solubility. So salts acts as a salting out agent to crystallize things. There are some organic compounds we also use, like ethanol, isopropanol, beta-butanol, dioxin. But mostly what they do, they change the dielectric constant of the crystallization solution, but they don't act as a salting out agent over here. The third candidate is polyethylene glycol. They are very large macromolecule, but they, like protein, they don't have any compact structure. So in solution, they are randomly oriented and take a huge volume. So they act as macromolecular cowding, and the protein molecules are being deprived from getting solution, so they are separated in the form of crystal. So these three compounds, they act in 3 different ways. And what you can do, you can use a combination of this thing, but if you use this is high amount, then you have to use this low amount, or this high amount, this low amount, high amount, this low amount, like this, because these two are not miscible. They are immiscible, so one has to be very low if you mix them up. So how crystallization occurs? So this is a phase diagram for crystallization. And suppose this is the solubility of the protein, and this is salt concentration of protein concentration. And so this is the curve is called saturation. This above this curve is protein is saturated, and below this side of the curve protein is soluble. This is unsaturated solution. And this side is saturation zone. And saturation zone, you can make 2 divisions. One is metastable zone, and that is labile zone. In metastable zone, the solution is supersaturated, but spontaneous crystal formation is not occur. But in labile zone, spontaneous nucleation can go. Or is if you you start with this thing and you go there, solution is supersaturated but no crystal. If you start from here and ultimately goes to this region, this level of supersaturation, you will get crystal, spontaneous crystal. But if your supersaturation goes very fast, like and it goes from this region, you will get a precipitate. So we need to control this thing and get our crystallization. So what happens in solution? Suppose we started with this solution, supersaturation was less, then we keep on supersaturating it by some means that will come later. So at some stage it will form a nucleus. And with more supersaturation, this nucleus grows, a bigger nucleus, and it forms a critical size. In that case, spontaneous crystallization can occur. So in the metastable stage, I think your solution is supersaturated, but seeds are very small or they don't grow spontaneously because they cannot cross this critical size and spontaneous crystallization can occur. Okay. So how do we achieve the supersaturation? We use this kind of plate. This is 24-oil plate. It's called limbo plate. Several other plates are commercially available, locally available like this. So these are oil, one oil say, and on top of this oil, you can grease it and put a cover slip. Now, if we cross-section this slide, it looks like this. So this is your oil, and in the cover slip, you take a protein solution and mix with a reservoir solution and tightly seal it. Then this compartment is an isolated system. So, and it is sealed also. So this there should be equilibrium between this protein solution and this reservoir solution. So how do we use the reservoir solution? Say high concentrated protein, say 4 molar ammonium sulfate we are using here. In the reservoir, we are using 4 molar ammonium sulfate. In the protein solution.
Slides not visible now.
Oh.
Suddenly from the round suddenly it started with that, but right now it's not visible.
So how to do can you see my slides? Hello? Is my slide visible?
Suddenly it's not visible. Maybe you need to share it again. Looks like.
Oh.
But is it possible?
Let me start again.
This one.
Mm-hmm. Now you check. Can you see the slides now? Okay. I think the slides are visible now. So suppose we have a 4 molar solution over here, and you mix equal amount of protein solution and this reservoir solution in the drop, and they are sealed. Now, what the Raoult law say? The Raoult law says that the partial pressure of a solution is equal to mole fraction of the solvent. Mole fraction times pressure of the solvent. So here the solution is 4 molar, so it will have less partial pressure, whereas here in the drop it is solution is 2 molar, so it will have more vapor pressure. That means it will produce more vapor, means water, and it will produce less vapor, but they are sealed and they are an isolated system, so they will try to equilibrate with time. So in this process of equilibration, what will happen? The solution water will come from here and it will be absorbed over here because it has a less vapor pressure and it has more vapor pressure. So gradually the drop will shrink.
Are you testing something?
No.
You see whether can they see now? Can they see? Can they see?
Nobody is answering.
No. Nobody is
You have to
answering.
see the chat box there.
They can hear what you are saying. Where is
And
the
they can
chat
hear
box?
me. But chat box will be with it all are unmuted. All are muted. No, they are not visible. 1740.
It will go once.
Visible now?
What document recovery that I'm not looking at the video? Save the files now, whatever you want.
Yes, I saved. Okay, you can answer and save it. No. You can hear me, no? Screen is not shared, so 1790. Output.
Do something with the file is the treatment problem.
Hmm?
Because it auto recovered everything.
Maybe I can save it now.
You say what?
Just wait for some time. Let it go. Oh,
This is the one you are
yeah, somewhere here.
getting to you now.
Oh. Okay. Let's see. Is it possible to see now? Hmm. Hello. Okay. Okay. Hmm. So let me repeat because some slides are visible. So it is a isolated system and use a drop with less molarity compared to the reservoir. So drop will have more vapor pressure, reservoir will be less vapor pressure, and that way the solution is water, oxygen and 2 hydrogen maybe. So this water is coming from this drop to the reservoir, and it's getting concentrated. See the size has reduced, and one stage you get the crystal. So this is one way of achieving supersaturation. That is in vapor phase. So like in sugar solution, you boil the sugar solution and bring it to the supersaturation and then do the crystallization. You cannot do it for protein. So this is the best way without hampering the native state of the protein. You can supersaturate the solution. So this is called hanging drop method because drop is hanging from the cover slip. Another thing, and you covered cover the well with the cover slip, but you use this kind of thing, and on top of this you can set the drop. So here equilibrium will, the water will come from here, will go over this, but here it comes like this. So the water movement kinetics will be really different, and moreover, this here your drop is hanging, so you cannot increase the drop size after some extent. But here you can increase the drop size and get crystal also, like but as otherwise the same. This is a concentrated reservoir, and this is half diluted protein plus reservoir, so there will be equilibrium and you will get the crystal. So this is crystallization is followed by the Raoult's law of vapor pressure. Now, suppose I have started from here, and I keep on telling that if you go there, you will get a saturated solution, but no crystallization, labile zone. If we go from here to here, spontaneous crystallization can occur. Go from here to here, precipitation occur. But how do we go from here to here? So this is presented over here. Suppose you start with a drop with a 3 protein and 3 precipitant. So your starting drop size is 6. And if you start with 4 molar ammonium sulfate in the drop, the ammonium sulfate concentration will be 2 molar, protein concentration will be 6 molar. So say after some time the drop becomes say 5.5, then protein concentration is 6.5, this is 2.2. So when it become 4, protein concentration is 9, salt concentration is 3. So with time, when it is 3, it is 12, 4. So with time, what you are getting, your protein concentration is increasing, salt concentration is also increasing. So this is this kind of equation. Suppose this is salt, this is protein concentration, so you'll get a y equal to mx plus c kind of equation. So suppose this is your starting point, this, and if you gradually come over here, 4 molar, somewhere here, the protein concentration is also high, so it will be somewhere here. So this is that's why I say y equal to mx plus c means this. If you start from here, it will go like this, depending upon the aim. It might go like this, it might go like this. So during this thing, equilibration, your protein concentration and salt concentration increases, and gradually you move from labile region to nucleation region or precipitation region. So how do you control this thing? Because this control, this is the main thing, how to control this thing. So suppose after something few days you see drop is clear. That means your protein concentration is or salt concentration both are very low, and you need to supersaturate it more. So you need to either increase the protein concentration or increase the reservoir concentration to move towards labile zone or nucleation zone. Or if you get precipitate, means your reservoir is too strong or protein concentration is too strong. This is different kind of precipitate. And sometimes you get spherulite kind of things. Spherulite means thousands of crystals clustered together, and they are very, very small, and they cannot be isolated. So it has to be you have to add some additive, or you have to slow down the process, or you have to change the temperature maybe, or reduce the protein concentration, and that way you can manage the spherulite and with the crystallization condition. Sometimes you get some needle, and from needle you need to increase the size either by reducing the salt or maybe protein concentration, or sometimes you can add glycerol as well. So glycerol has two kind of things. Actually, it increases the solubility of the protein, and another thing, when it forms crystal, one protein molecule comes and sits on the nucleus maybe. So this is a diffusion control reaction. And diffusion control reaction, if you change the viscosity, like adding glycerol or something, the process will be slow, and you might get better crystal or bigger crystal. So this is, so far today, we said the drop in hands, but in modern day, what we do, we use this kind of thing because it's very tedious to set a drop in 24 well, and so in that way you need more protein first of all, it is more tedious, and you need more amount of protein, salt, etc. So this is a liquid handling system. This is picture is taken from Hydra, one company like this. There are several companies like Mosquito and those other things. In modern day crystallization, what they do, they have a syringe, 96 volt syringe, and this is a 96 volt plate. So this is your precipitant, so 96 kinds of precipitant there. That is, these are all commercially available, 96 volt precipitant or so. So you first you use the syringe, this syringe. Then with the syringe you take your protein and put in this 96 one. Then you add this 96 kind of precipitant, and that 96 well can be used again after washing on the 96 well crystallization condition, crystallization trays. So you can mix them and wrap it with the plastic thing. So you can cover this, and equilibrium goes. So in that way, you can maybe in few minutes you can save some 96 or 100 drops in few minutes, and you need very less amount of protein, very less amount of other reagents also. But once you keep on watching this tray, and if you see some condition is there, in that case you can go back to the linear plate, and because here the crystal, even if you see the crystal, it will be very, very small amount. So what you have to do, you have to scale up the procedure, and for that you need to go back to limbo plate and set this kind of the exact condition over here in the limbo plate, or some variation of this, because during scale up there might be some change, and you get the crystal for. Okay, so this is roughly about crystallization, but there are some other parameters also that can affect the crystallization, like magnetic field or electric field, and this is recent development, and maybe microgravity also can change your crystallization condition. Recent development is electric field or magnetic field, and I can tell you one story that while I was in postdoc, one of my friend was crystallizing the protein, but in the cover slip he was used to crystallize, he used to keep it in aluminum foil. And one day I asked, why you are keeping it in aluminum foil? Then he told us, while I prepared the cover slip for crystallization, and during rubbing and this thing, it develops some static charge. And if I set the drop, I see in my case, the crystallization hampers. Then I told, why in aluminum sheet? Then he told, aluminum is a metal. So aluminum foil, you keep after preparation of cover slip, you keep the cover slip in aluminum foil, and you discharge it, the charge goes, static charge goes, then you set the crystal. And I was surprised at the time, but recently I see that charge also can hamper crystallization, or you can change the number of crystals by applying static charge or dynamic charge. And similarly, microgravity can change also crystallization, because to crystallize something, then there is the concentration variation in the drop, and if there is gravitation or there is no gravitation, that can affect the concentration difference and convection current of protein in the drop. So this is about my crystallization. During the course designing, I thought that I'll go for some lab visit or lab demonstration kind of thing. But later I saw this is not possible. So I am giving some example that I have faced in my lab during crystallization. That will be helpful maybe. Before that, let me allow you to go back to some previous slides. If I am here, say somewhere here, what I told us, in this region, no spontaneous nucleation occur, and even the solution is saturated, you won't get crystal. But if from outside you supply some microcrystal or something, then that crystal can grow. This is the situation occurred over here. This is a trypsin and inhibitor complex. I got crystal like this, very ugly looking crystal. But later, after different trials, I didn't get any crystal. The PEP was different, obviously, might be that was the reason, but it gave me hard time to get reproducing this crystal. Then what I did, I set crystal with this same condition, and say in some 10 drops, and after 3 or 4 days, one drop I touched the crystal and seeded it. Then 4th day or 5th day, another drop I seeded it. Then 7th day, another drop I seeded it. So in that way, on 8th day, I saw the seed, they grew up. I touched the crystal drop over here. I touched the crystal with loop, and another drop I touched over here, and from away from this thing, I see nice shaped crystal, triangular crystal as there. So this is kind of microstudy. So you take the seed from here, put in your that solution that was saturated but not produce any kind of nucleus. So you externally supply nucleus and you get the crystal. So this is called macroseeding. Okay, this crystal, this is a ribokinase crystal. I was getting crystal, but size was very small. Then, and not only small, after some time the crystal growth was ceased. So with the old, and it was in the drop crystals, the crystal came at about 10 days or so, maybe a small crystal. So after that I wait for another 10 days, but there is no improvement, rather it was. So a 20-day-old drop in the fridge, I ran a gel, SDSP gel. This is SDSP, native means without BME, it is with BME. Level is low. There is no BME means if there is a disulfide bond between ribokinase molecule, then that will show. But if you apply BME, then it will break the dimer to monomer. That's happened, you see the old drops, it has a dimer, but fresh drop, it is mainly monomer. But old drop, it is monomer dimer mixture. So I thought this is hampering the crystallization. So what I did, I applied more BME or DTT in the drop and also in the reservoir. And later on, I got beautiful separate chiasm that diffracted up to 2.5 angstrom. During my presentation, I talked about some chemical modification thing. This is a transcription terminator inhibitor protein. Every time I was getting this kind of needle, which is very disappointing. Even several trials we got this thing. Then we saw there is a conserved cysteine residue in the molecule, probably 2 cysteine residue, but they are not in a position to form dimer, because from related structure I saw they cannot form dimer. So maybe there is some modification in the cysteine, or they are hampering the crystallization formation. So what we did, we modified the cysteine with iodoacetamide. Iodoacetamide, so if you reduce your protein, you say make all cysteine to SH, then add iodoacetamide, so it will form a covalent bond with the cysteine sulfur residue. So they can never form a dimer with other molecules. So after applying this and applying glycerol on this thing, I could improve from this stage to this stage, but surprisingly, this crystal diffracted up to 1.7 angstrom, and we saw the structure. So this is an example for chemical modification. This is, for example, for disulfide modification. This is an example for seeding. And this is another crystal. This is EL domain crystal, EL protein. It hydrolyzes CDIGMP. It binds CDIGMP over here, and CDIGMP is a huge molecule. It covers this position. So while we purified this protein, the solubility was very low, it's 1 or 1.5 mg per ml. That is not amenable for crystallization. So we could not crystallize this that time. We could not even set the crystallization drop, and the solution was highly impure. So impure means it forms different kinds of aggregates probably, and after some time precipitates. But the purity was very good actually. Then we saw this protein also has some cysteine. So one cysteine I somewhere here, we mutated to serine, and so that stopped the oligomer formation. But even then solubility was very less, around 2 mg per ml. Then we added calcium. Calcium binds somewhere here. After adding calcium, we got the solubility around 6 mg per ml, and we saw it drop. Even if we add CDIMP with this thing, solubility increases further, but we need to for the apocrystal also. So without CDIMP, but calcium, after adding calcium, we can crystallize apoform, and it is very hard. CDIMP bound form or CDIMP coated bound form, various kinds of form we could crystallize. So here metal ion, I would say, metal ion changes the scenario. Solubility was very less, but if you add metal ion, that increases solubility, and there is a cluster of positive charge also, negative charge also. So if there is no system, metal ion, they will repel each other. So this portion of the structure will be flexible. And this loop, particularly this green kind of loop, this will be very flexible, and that will hinder crystallization or solubility as well. So this is an example of use of metal ion during crystallization. Okay. Finally, what I am going to show is that we are working with the acyl phosphate protein that Professor Chakraborty also told. So this is acyl phosphate means hydrolyzes acyl phosphate group to acyl group and phosphate. So we release the inorganic phosphate. In case of Vibrio cholerae, VCACP, its 20th residue is cysteine, and it is not catalytically active. But if we mutate the 20th residue to cysteine, and cysteine to arginine, then this becomes VCACP C20R. This is highly catalytically active. This form we tried to crystallize initially. So this is ACP C20R, highly catalytic active. This is not. We tried to crystallize this thing, and for about 6 months or so, there is no result. Then we went for DLS. For DLS, it gives you the oligomerized state in solution. And in solution, you see there are three kinds of defined population. One is small molecule, and this is little higher, and this is further higher. So this, if we determine the radius of this thing, this corresponds to ACP trimer, this corresponds to ACP hexamer, and this corresponds to ACP dodecamer. So if the solution is that heterogeneous with three different kind of population, it is no wonder that we are not getting any crystal. So what to do? In this meantime, we prepared this thing, ACP320R, and it crystallized, and this dimer, the size of this dimer is close to this. So this is ACP dimer. We can guess this is also C20 BCACP dimer. This is BCACP C20R dimer, but this solution is heterogeneous. But we are curious, what is this portion, or what is this Hughes entity? If you run SDA specs, this is single band. But if you do DLS, you see three different bands. That means in solution, you have three different populations that are originating from VCACP itself. So VCACP trimer, hexamer, or dodecamer. So we show this is dodecamer. The size is so big, what is happening over there? So we wanted to crystallize it. Then, but how to achieve this thing on only the dodecamer? So we did some experiment. We added different kind of salt in the protein and did DLS. Then we see that if we add any tetrahedral anionic atom, an anionic molecule in the protein, we see this. Say this is trimer. If we add say 0.4 molar this thing, ammonium sulfate or vanadate or tungstate, any tetrahedral anionic atom. See gradually, if we increase this concentration, the tetrahedral anionic atom, we see this concentration of trimer is decreasing. So at 0.6, we have only hexamer and dodecamer. If you come over here, 0.8, we have no trimer, no hexamer, but all dodecamer. So you can use 0.8 molar AMS with this solution. So that will convert all these 3 different oligomer to a dodecamer, and we try to crystallize that. Okay, so we got this dodecameric structure. This is a cage kind of structure. Cage in the sense there are 12 marks shown in different color. They form a cage kind of thing, and inside the cage is hollow. So this is a nano cage kind of structure. So it could be a container. Either it can entrap some molecule inside the cage for future use, or it can bind some molecule on its surface, and it can act as a carrier. So this is an example that I was telling that the solution is pure, but solution is homogeneous. Is not homogeneous. Here the solution was pure. SDS page it was single band, but solution was heterogeneous, and you try to remove the heterogeneous and either trimer or hexamer or dodecamer, which form you want to use, you can crystallize that. So this is an example of variation of this thing. So this is the crystal we got. It's a nice looking picture. Okay, so these are the books you can consult for your future study.